Hello everyone, this is for the Chapter 6 Revisit packet. Trying to go back and clear up some misconceptions from Chapter 6. The first thing that I want to do is ask you guys, if you have this equation, and I'm asking you to find the x-intercepts, the first thing you can do is graph it, and you look at it. So here's an x-intercept that's sitting at 3, and then here's one that's sitting as a fraction. One way to go about this, to find that fraction, is to do what was called the rational zero theorem. And we'll talk more about this as we proceed through the slides, but jumping to it, the rational zero theorem was you take all the factors of this number, so plus or minus 1, 3, 5, and 15, and then you divide it by all the factors of the front, plus or minus 1, plus or minus 2. And looking at this, looks like negative 2 point something. Well, right here is negative 5 halves. And it turns out that we haven't proved it yet, but I'm just using this to explain the rational zero theorem. You can use this to find rational zeros. Now, to explain rational again, rational is any number that can be written as a fraction. Square root of 2 is not rational. It can't be written as a fraction. It's a non-repeating, non-terminating decimal. So these are not rational. They're irrational. Irrational. Okay? Anything that involves I, of course, is imaginary. So the rational zero theorem just applies to ones that can be written as a fraction. And notice 3 over 1, is also a rational number. So it also found the other one. Now this doesn't work on all graphs. I'm just using this to go, hey, to find the x-intercepts, you can use the rational zero theorem to help you get ones that are fractional. It can also help you get ones that are whole number too, but those are usually much more obvious. All right. I asked you to find all the zeros. So the first slide I asked you to find x-intercept. Now I'm asking you to find zeros. Okay? And I'm suggesting the first step you do is you factor it. And with all the work we just did on factoring, this one shouldn't be so bad to factor it. We're just going to apply what we know. The first term, or the first term right here is going to be 2x. The next one's x. They have to multiply to 15. So I'm going to try 5 and 3. They're going to negative 15. I'm going to try plus 5 minus 3. So this is my first guess. Then you check the O and the I of FOIL. So outside, minus 6x, inside, 5x, and you get minus 1x. So you got the middle. So this is the correct factorization of this polynomial. Now I'm asking you to find the zeros by factoring. Notice you've got something times something equals 0. So if I just kind of symbolize it, something times something else equals 0, the only way you get that to happen is if either one of them is worth 0. And that's the same idea here. It's called the zero product property. If you've got something that's a product that equals 0, one or both of them have to be worth 0. So subtract the 5, divide by 2. Whoops, divide by 2. X is equal to negative 5 halves. Add the 3, x is equal to 3. And if we could just hop back the screen, no doubt, negative 2.5 and 3. It worked. You factored it, so instead of doing the rational zero theorem, which worked, instead of doing that, you factored it and used the zero product property to set each factor equal to 0, and you found the zeros. So in this case, x-intercepts are the same thing as zeros. So if I ask you to find the 0, one option is factor it, do the zero product property, and then you have the zeros. Okay? Find all the zeros of this thing. Well, factoring this one would be a little bit harder, and the idea is it's called extracting the root. The difference between this equation and this one is I hope that you see the middle term, the b. So if I think of it as ax squared plus bx plus c, the b is missing. It's not there. It's like ax squared plus c. Okay? There's no middle. When that happens, the easiest way to do it is just solve it. And what do I mean by just solve it? Add the 5 over, and you have x squared is equal to 5, and then take the square root. Don't forget, when you put an even root on the page that wasn't there before, a plus and minus shows up. So you have the square root of 5 and negative square root of 5. You have two answers. You don't have to write it like this. I'm just doing it to illustrate the point. Some kids are a little unsure what that plus and minus means. It's two answers. Okay? So that would be finding the zeros. You extracted the root. That's the technique that it's called. Okay? So here, what if you're told the x-intercepts or the zeros, and you're asked to find the polynomial? So let me look back at this one for a second, the first one we did. If you factored it, plus 5, I believe was it, at x minus 3. Then you set each of those equal to 0, and you get x is equal to 3, and x is equal to negative 5 halves. Notice that if I just back up and do it a little more thorough, I know you guys can jump ahead that fast, but I'm just doing it to be thorough. I have 2x is equal to 5. So notice I changed the sign on the 5 to move it over. Whoops, changed the sign on the 5 to move it over. And then I'm dividing by 2. And I'm really illustrating that point that you divided by 2. That's how you got the 2 on the bottom. It was the coefficient on the x. That's where it came from. Okay? So the connection between zeros and x-intercepts and the factors, okay? This is the factor of that, and this is the factor of that. Notice any denominators are coefficients, and then any numerators are opposite in sign to what this number is. Okay, so if I put that over 1, it even works for this one. 1 is the coefficient, and you change the sign on this number. So if I gave you 7/3, it as a factor would be 3x, and then change the sign, minus 7. If I gave you negative 5/4, the 4 goes in front as the coefficient, and change the sign. That would be the factor. Okay? So here are some zeros. Give me the polynomial. Well, you have to start by writing the factors. 3 goes in front as the coefficient. Change the sign. This one, 1 is the coefficient. You don't need to write it. Plus 5. Now I'm asking you to FOIL it out. So that would be 3x squared plus 15x minus 2x minus 10. And then you just add the like terms in the middle. There you go. Okay. This one, you're going to have two factors. So that would be 5x plus 3 and 3x minus 4. FOIL it. 15x squared minus 20x plus 9x minus 12. So you have 15x squared minus 11x minus 12. All right. So far, so good. What if you have these? It doesn't say that it has to be, the number on top is what I was saying. The number on top, change a sign. The number on bottom is the coefficient. So I know it's square roots and you make it a little nervous, but it's just x. Change the sign. Oops, square root of 5. Just x. Change the sign. Now, if you need to FOIL it, go ahead and FOIL it. I would love it if you recognize this is the difference of square pattern. So you square the first thing minus square the second thing. There it is. So this is actually the third problem we did. I think if we back up, there it is right there. Okay, and those were the zeros. Okay, so coming back. Okay, if you need to FOIL it, by all means FOIL it. X squared plus square root of 5x minus square root of 5x, and then there would be minus square root of 5 times square root of 5 is 5. These two are opposite in sign, so they cancel out, and there it is. But I'd also love it if you recognize that as the difference of square pattern. Square the first minus square the second. Done. Okay? This, so if you here you have 4 zeros. So to write them all out, I guess I'll start at the beginning if I erase that. Okay. Good. So you'd have x minus 2, 2x plus 3, and then x minus the square root of 5, x plus the square root of 5. Right? These two we just did. They're right here. So if you want, we can just write that. We know what the answer to that's going to be. So then we got these two. Oops, 2x plus 3. If I was multiplying these together, I'd go ahead and get these two and then multiply it by that. So you'd have 2x squared plus 3x oops, minus 4x minus 6. So then you'd have 2x squared minus 1x minus 6 times x squared minus 5. Now, you guys are welcome to do the distributive property. Okay, so you'd multiply this all through. So how about we go 2x to the fourth minus 2x squared minus 6, it's cubed. Holy cow. That times this will give you a cube. Okay, and then minus 6x squared. Then you take the negative 5 and run it through. Now I'm going to line these up to help me collect things. Minus 5 times 2x squared would be minus 10x squared. Then minus 5 times minus 1x would be 5x. And then plus 30. So I line these up so I can just add them together. So the answer is 2x to the fourth minus 2x cubed minus 16x squared plus 5x plus 30. Okay? Some of y'all like doing the box method. You're welcome to do the box. Or the lattice method, depending on how you guys were taught the word, the process. And then you just multiply this out. So that'd be 2x to the fourth minus 1x cubed wait, do I have a mistake here then? I do, right here. Okay, minus 1x cubed. Y'all should have spoke up. I just didn't hear you. Apologize for that, so that changes this one. Sorry, guys. Making arithmetic mistakes already. Hey, but at least I caught it. Minus 6x squared. Then that would be minus, whoops, can't read that at all. Oh my goodness, so that would be minus 10x squared. And that would be 5x and 30. And now you just collect like terms. There's the 2x to the fourth. There's the minus 1x cubed. This would make minus 16x squared plus 5x plus 30. So there it is. Okay. To get the next one. Okay, this. Change the sign. X plus 4. Then x minus 3i. And x plus 3i. I would suggest you multiply these first. You guys recognize this as a difference of square pattern. They're the same, but one's plus, one's minus. So you square the first thing, minus square the second thing. And you guys need to remember I squared is negative 1. So that's x squared minus 9 times negative 1. So that's x squared minus a negative 9. So it's x squared plus 9 times x plus 4. So now you just FOIL it. So x cubed plus 9x plus 4x squared plus 36. And then all you have to do is just rearrange the order. Plus 9x plus 36. So there's the connection between zeros and factors and how you get the polynomials. Right? So going through what we just did on the very first problems, wrapping things up a little bit, to find the x-intercepts, given this, we started out by graphing it, and then we actually did the rational zero theorem to find it. We factored it and set those factors equal to 0 to find the zeros. The only thing we didn't do was the quadratic formula, but you know that that is an option to find zeros in doing this. And remind you what the quadratic formula is. There it is. So all four things here are a game to solve these because it's degree 2. Now, when it's larger than degree 2, then these same four things are options, but the order you do them is much more prescribed. It's much more rigid. The first thing that you'd want to do is the rational zero theorem, and then graph it. Now, debatably, it's debatable which one of these you do first, but for sure, you're going to do one of these two first. The order, which one's one, which one's two, there's some flexibility. Okay, I prefer to do this one first before you graph it, but that's just me. You can graph it first, then do the rational zero theorem. But before you go on, both of these need to be done, okay, when the degree is larger than 2. Okay, then you inspect the graph, and this is what's different from this up here now. You inspect the graph and divide out any x-intercepts that you got from the rational zero theorem that you can find. Once you get it down to degree 2, then you have the choice to either do the quadratic formula or factor it. Okay, so let me walk you through that. So here goes. First thing I said was do the rational zero theorem. So I got to get all the factors of 24. So plus or minus 1, 2, 3, 4. Sorry, that's a 4, 6, 8, 12, and 24. That's a 4 again on that, over all the factors of the leading coefficient. Now, to write them out, it would be all of those over 1. Oops, come on, go away. Plus or minus 1. Come on. Don't tell me you just died. I don't want to hear that. That would be bad news. Okay. Crying, I did. Plus or minus 1, 2, 3, 4, 6, 8, 12, and I'll just write it over the graph, 24. But then if the bottom is 3, you have plus or minus a third, plus or minus 2/3, plus or minus 4/3, plus or minus 6/3 is 2, so I need to write that 8/3. 12/3 is 4, 24/3 is 8. So those would be all your possible zeros. Now looking at this, that looks like -2. That looks like the only thing near 1 and something would be here. So positive 4/3, and then this would be 3. If you didn't have the rational zero theorem to show you this number here, is that 1.5? Is that 1.3? Is it 1.4? Is it some other decimal? You don't know. But this is where this comes into play. Then what you should do is set your table up to check these numbers to see if they actually work. So you should get 0. And then you try 4/3 and you try 3. These indeed do actually work, and I wish I could do it interactively here to show you that they're actually working, but the software won't record it. So suffice it that you need to go to that step and set up your table and check them on your table. Okay? You found them all by doing the rational zero theorem and graphing it, which, backing up, that's what I suggest you do here. You do these first two and do it. Well, the question then comes, well, what if they all don't appear, or you can't get them from the rational zero theorem? That's when the other steps come into play. So here's one where they don't all show up. Okay, you have 3 x-intercepts, don't get me wrong, but you can't get them from the rational zero theorem. So let's set it up. Plus or minus 1, 2, 4, 5, 10, and 20 over the plus or minus 1 and 3. Okay, being thorough, I'm just going to write them out. I know I told you guys you could quit right here. I'm just doing it to illustrate a point in case that idea is a little rusty for you. And then you'd have 1/3, 2/3, whoops, forgot the plus and the minus, plus or minus 4/3, and plus or minus 5/3, 10/3, and 20/3. Looking at the graph, not so sure what that one is. We'll hold off. This one, so 1, 2, and a little bit. -2 point something. That's 3 1/3. That's 1 2/3. And that's 1 1/3. Okay. And that would be 6 2/3. I don't have anything from the rational zero theorem to give me this one. I don't have anything from the rational zero theorem to give me that one. This one sure looks like 1 1/3 or 4/3. Okay, that one looks like 4/3. Let me erase it, clean it up a little. Yeah. Okay. And you check it on your table, and sure enough, it works. Okay. I can't find them all. These other two aren't showing up with the rational zero theorem. So I did the rational zero theorem, I graphed it, I inspected it. Now what I have to do is divide out any x-intercepts I can find. It's degree 3. If I can get it down to degree 2, then the quadratic formula is fair game. So that's what I have to do next, is divide this sucker out. I have to divide out 4/3 from 3 minus 4 minus 15, 20. Drop the 3. That'll give me 4, which gives me 0. 4/3 times 0 is 0. Minus 15. 4/3 times minus 15 is minus 20. And 0, which you should get a remainder of 0. Now, here's another piece. Because you divided something with synthetic division, that's what this was, dividing synthetically, and it had a denominator. I have to divide out whatever numbers are here by that denominator. So I get 1, 0, minus 5. That's actually your answer. I mean, not your final answer total, but that's the answer from the division. Whenever you had a denominator and you're doing synthetic division, you have to fix the shortcut of doing synthetic by dividing everything by the denominator. So this gives you x squared minus 5. I need to find the remaining zeros. Now now set this way back to a previous one we did, right here. This, I need to find the zeros. So what did you do? You added the 5 and then took the square root. So you got x is equal to plus or minus 5. Oops, square root of 5. Coming back to this, you need to find the remaining zeros. The remaining zeros can be found here. You could do the quadratic formula, but because b is missing, so again, because b is missing, you can do the quadratic, but it's more work than if you just add the 5 and take the square root. So these two numbers, that would be negative square root of 5 for this one, and this one would be positive square root of 5. And you can always go and check these on your table by typing in the square root of 5, and you should get 0. And negative square root of 5, and you should get 0. Okay? If this had a value of b, like x squared minus 2x plus 5, then you do the quadratic formula and get your other two answers. Okay? All right. What I'm needing to work with you guys on in this last slide is identifying how many rational, so again, those are things that can be written as a fraction, whether it's a whole number like 3 or a fraction like negative 3/2, irrational, anything that's a square root, or imaginary, anything that involves I. How many of these things do you have? Okay, it's degree 3. I'm looking for 3 zeros. The degree tells you how many zeros you're looking for. This one, they all are showing up. They all are hitting on whole numbers. So there's 3 rational zeros. Given this equation, there are 3 rational zeros. Okay? Assuming it's the same equation for this graph, so you have x cubed plus 3x squared minus 4x plus 2. This equation doesn't do it, but just assume it did. Assume it made that graph. So I've got -1 and then 2 fractions. Now if I set up the rational zero theorem on this, I've got plus or minus 1, plus or minus 2, over plus or minus 1. The only number that's working from that list is -1. I can't get any fractions from this. So these two have to be irrational. They have to involve a square root, just like this one did. because those numbers did not show up in the rational zero theorem. They were not a part of this list. They're still real numbers. They're not imaginary because they're showing up as x-intercepts, but they're not in this list, so they have to be irrational. Oops. So here, because these two numbers are not showing up in the rational zero theorem, they have to be irrational. So I have one rational, two irrational. Two irrational zeros. Okay, now this one, assuming it's the same equation, there's only one rational zero showing up. One rational. No others. The ones that, now I'm looking for three of them because the degree is 3. That automatically means you're going to get 2 imaginary zeros. The quantity of imaginary zeros you're going to have is 2 because they aren't showing up as x-intercepts at all. That brings up the next point is, if you can see them, all real zeros are exactly the same thing as x-intercept. Real numbers are rational and irrational numbers because they don't have I. Anything that has an I is not an x-intercept. Okay? Imaginary zeros are not x-intercepts. Okay? I know I need 3. I can only see 1, so I gotta have 2 imaginary. Okay? So, backing up, these are the order of things that you're going to go through. Rational zero theorem, graph it, inspect the graph. If you can find them all, great. That's what happened on this one. We found them all, fantastic, no division was needed. But you still needed to check them on your table to see if they worked, to make sure they worked. If you can't find them all, then you have to divide them out, like we did here. Look at what's left, and you have the choice. You could factor it, you could do the quadratic formula, or in this case, we extracted the root. But the point being, you had to get it down to degree 2, so you had some other tools you could use. Okay? So that's the recap of Chapter 6.